Okay, so I'm going to be studying hydrology and fluvial geomorphology. It's quite late right now, so I might mess up a few words. Just bear with me. If you want to follow along, here is the not schedule, but here are the topics I'm going to be going through. So I'm going to start with stores, then flow types, underground water. You can read the rest. You can pause the video and read the rest if you want to. I'm just making a video about this because I don't want to sound like a madman talking to myself at almost 2 in the morning. So yeah, time to study. I'm also going to be just drawing in paint, just to help myself understand topics, and if you also want to understand the topic, you can just pay attention. Okay, so hydrology and fluvial geomorphology. I'm going to start with stores. Okay, so there are a few different types of stores. Let's start with interception. So we can think of interception as, let's say there is a tree. Wrong color. Let's say there's a tree or a bush over ground. So the definition of interception is precipitation caught and stored by vegetation before it reaches the ground. So let's say it rains. This rainfall or the moisture with water from this rainfall gets caught by this bush or tree and it doesn't reach the ground. So that is interception. Moving on, we have surface water. Surface water occurs when infiltration capacity is exceeded. This causes water buildup on the surface. Okay, I'm just going to use the same diagram. So let's say it rains again. The soil is saturated, which means that water can no longer infiltrate into the soil. This causes water buildup on the surface, and this buildup of water is called surface water. Okay, now let's move on to temporary stores. So a temporary store is something like a puddle. So a temporary store is something like a puddle. So you can think of temporary stores as just puddles on the ground. They won't be there forever. They will disappear eventually. That is why they're temporary. Then we have permanent stores. So permanent stores are stores such as wetlands, oceans, and lakes. They are those, you can say, big puddles that don't dry up. Okay. Now we have groundwater. So groundwater is water that is percolated into the bedrock. So here's the surface. Here's the bedrock. So groundwater is the water that has infiltrated into the soil, gone through all the soil, and then gets stored in this bedrock. So bedrock is just the very hard rock that is deep in the ground. Yeah, that's basically it. And we can dig wells into this bedrock. And this bedrock normally sits at the water table. So there's always water here, along here. And us humans can dig wells below bedrock to access this water, which can then be pumped back up to the surface. And then we drink that. So that's groundwater. Groundwater is just water that is percolated into bedrock. Okay, now we come to channel storage. So let's add a little part here. So channel storage is just water that is stored in a river. So here's the river. It's just the water that gets stored in that river or stream or whatever man-made drainage channel. It's not too difficult to understand. And then the final store that we need to know is soil moisture. So there's not any empty space between the surface soil and bedrock. This is all filled up with other pieces of soil and rocks and whatever. So in between these soil particles there is space, and this space can be filled by, or these small gaps can be filled by water. So when this occurs, it increases the soil moisture level, and eventually this will cause the soil to become unstable. Soil moisture is different in different soil types. So for instance, sandy soil is similar to what I just drew. So sandy soil has large pores. This means that there is a lot of space between each sand particle. As you can see here, a lot of space. This means that sand is permeable and there is quick infiltration. So when it rains on the sand, the water infiltrates quickly. However, soil types such as clay are hygroscopic. It's quite difficult to understand, but basically that means that if you have a clay particle, and it interacts with water, the clay particle will grow in size and consume that water. Okay, that's basically what hygroscopic is. And eventually, once this clay particle has absorbed this moisture, it becomes impermeable. And because clay particles are very close together, as you can see in here, once they've expanded and absorbed all their water, they become impermeable and water can no longer infiltrate into them. And this causes buildup of surface water. And this brings us to flows. Okay, so flows. I'm going to start with the flows that occur above ground. So let's say this is the ground again. So first we have throughfall. Throughfall is just, here we have a tree. Yeah, the tree's a bit scum, but yeah, here we have a tree. Throughfall is water that has fallen onto the tree and then drips off of this tree into the ground. So it's the water that interacts with the tree, drips off the leaves, and then goes into the ground. That is throughfall. Then we get stem flow. Stem flow is pretty similar. However, this occurs when the water from the tree goes down the stem or trunk of the tree and into the ground. So if you ever get asked stem flow in the exam, just think of what a stem is and then just say that the water flows down that stem and you should get your marks. Okay, so now we get to overland flow. I'm tired. Now we get to overland flow. So overland flow occurs when the soil is saturated or when precipitation exceeds the infiltration rate and surface runoff occurs. So overland flow occurs when there is a lot of rain or rain for a long time and the soil below the surface becomes saturated. Saturated soil is basically just soil that can no longer absorb any moisture. So when this happens, there is a buildup of surface water. So there's a buildup of surface water, and once this buildup becomes great enough, overland flow will take place, which happens. Well, overland flow is basically just this water flowing over the ground. And then extreme overland flow is called Hortonian flow, and this is shallow laminar flow that causes a lot of erosion. You can think of Hortonian flow as a flash flood, for instance. So it occurs when there's a lot of surface water. And then there is very quick flow rates above the ground, which causes erosion. So yeah, that's overland flow. And then finally we get channel flow, which is quite easy. So channel flow is just water that flows in a channel. So if you have a river, it's the water that flows down that river. If you have a stream, it's that water that flows down the stream. And yeah, you also get the man-made channels, so it's just that water that flows inside that channel. Okay, now we get below ground. So I'm going to start by just drawing the surface. So below ground, we can start with infiltration. So infiltration is when precipitation is absorbed into the soil. I really need a bioblast. Yo, I'm tired. I'm gonna get through this, it's fine. So infiltration is when precipitation is absorbed into the soil. So let's say it rains, this water will interact with the soil and then it will infiltrate into the soil. Okay. Moving on, we get percolation. So percolation is the slow movement of water downwards through the soil and into bedrock. So let's say this black line here is bedrock. So infiltration occurs up here, above ground into the ground. Percolation occurs once infiltration has occurred, and it is just the water moving downwards into bedrock through the soil. Bedrock is just, you can think of bedrock as very dense soil and rocks deep below the surface. So percolation is just flow between the surface and bedrock. Okay. Moving on, we get to the horizontal flow types. So these two flow types are lateral. Not lateral, I mean vertical. So infiltration and percolation are both vertical, which means that they both occur in the vertical plane. The next few are going to be horizontal. Let me just quickly draw another quick diagram. There's the ground, there's bedrock. I'm going to start with through flow. So through flow is water that flows through the soil between the surface and bedrock. So here's the surface, here's bedrock. Through flow is the water that flows between bedrock and the surface. So it's not above. Above the ground is overland flow. It is the flow that occurs between bedrock and the surface. So it's through flow. It flows through the soil. Okay, next we have groundwater, which isn't really a flow type, but it brings us on to the next flow type. So groundwater is just water that has infiltrated the ground and has entered the water table. So the water table is usually around bedrock, quite deep down, and you might get asked what the phreatic zone is. The phreatic zone is part of an aquifer, which is an underground layer of water made up of porous stone, earth or gravel. So the phreatic zone is basically this layer here. It's just run about the water table. So I'm getting sidetracked here. So groundwater is water that's infiltrated the ground, that has entered the phreatic zone or entered the water table. So groundwater is just water stored underground. It's basically it is quite easy to understand. It's just water stored deep down underground, round about bedrock. Okay, and now this moves us on to base flow. So base flow is when underground water seeps into a riverbed and contributes to the discharge. This occurs very slowly and can take months or even years. So here's the groundwater. This groundwater will slowly move in a certain direction. Doesn't matter which direction, but it usually moves towards more water. So it moves, and then eventually it will join a riverbed. So here's a river, and then once it has joined this riverbed, it will sometimes form an underground river, which I'm sure you've heard of before. So an underground river is just a river that flows underground. So it's a lot slower than an actual river, but its fundamentals are the same. It's just water flowing downstream together. Yeah. Okay, so what's next? Next is the water table. So this is no longer what's it called? This is no longer flow types. This is just underground water. So we have the water table. The water table makes up the upper level of the phreatic zone. It will rise and fall depending on the amount of rainfall percolating downwards and the amount of base flow from lower rocks. So the water table is just this area here. Phreatic zone is roughly just, the phreatic zone is just this level. Like, you can just think phreatic zone this level. If you get asked it, just say it's similar to water table. You might get 1 mark, might get 2 marks. But just say, yeah, just say that. So water table is collection of groundwater, top of phreatic zone, that is influenced by the amount of water coming down from rainfall and the amount of water coming up because of base flow. Okay, now I'm going to move on to groundwater recharge and groundwater loss. So groundwater increase and groundwater decrease. So on this side I'm going to have increase, this side I'm going to have decrease. Okay, so it increases because of infiltration. It increases because of seepage. So seepage from river banks, the beds of rivers, puddles and lakes. And it increases artificially. So groundwater recharge occurs because of infiltration, seepage, and artificially. Artificially, it occurs from irrigation and reservoirs. Those are the two main ones. So there you go. There are 3 reasons why. And then groundwater loss occurs because of evapotranspiration. So let's say there's a drought. This water from deep down will go up to the surface and evaporate and move on to another area. Natural discharge, so groundwater, it will just continue flowing downwards into, let's say, that underground river as mentioned before. That's just discharge. Leakage or outflow, yeah, it just goes somewhere else. It just moves along. As said before, it just joins another river, joins another basin, joins something. And then the main reason that groundwater loss occurs is artificially. So groundwater is the water underground. Because humans are greedy, we want this water. So we dig wells and reservoirs into this water, and we suck this groundwater out of the ground and take it away from the area. This causes the water table to drop and it to be less groundwater. And then we complain about droughts and trees dying and not enough water and rivers and everything. Yeah. Okay, now let's move on to aquifers. So aquifers are permeable rock like sandstone, limestone, and chalk that contain significant quantities of water. Water inside aquifers moves slowly and maintains stream flow by absorbing or releasing water in wet and dry periods. So aquifer is just deep down in the ground. Let me start drawing in blue. I don't even know why I started drawing in red. So aquifer, water underground. Water underground. This water is stored in permeable rocks like sandstone, limestone, and chalk, and aquifers are only classified as aquifers when they contain a lot of water. Okay. The water inside aquifers is never stagnant. It is always moving. Even though it is moving very slowly, it is always moving. And it moves because of wet seasons and dry seasons. So let's say there is a lot of rain. It will move. It will sink further down into the earth, into bedrock, because there is more water. In dry seasons, the aquifer will reduce in size because the water is needed elsewhere and it is absorbed by the drier soil above. Okay, and now we get to springs. So springs are quite easy to understand. Here's the ground. Here's the groundwater. So a spring is underground water flow that reaches the surface. So here's the underground water, here's the surface. A spring is just when this underground water reaches the surface. So it occurs when this underground water is either very near to the surface or when only just a part of the spring or underground water goes up to the surface. That is a spring. It occurs where percolating water reaches an impermeable layer or saturated zone. So you can think of it as groundwater here is moving along this way and it gets trapped by rocks like this and impermeable, remember, impermeable, and then it gets forced up and it causes a spring. Okay, now let's move to discharge. So I'm going to be talking about the hydrograph. So you get two types of hydrographs. Let me quickly see if I can find a picture of one. Okay. Let me use this one. This one looks quite easy. Copy image. It's going to be bad quality, but who cares? There we go. Hydrograph. So we get two types of hydrographs. We get an annual hydrograph and a storm hydrograph. The annual hydrograph is used to study the responsiveness. I'm tired. I can't even speak. The annual hydrograph is used to study a river. What am I saying? The annual hydrograph is used to study the responsiveness of the river to its environment. Okay. So, I don't even know why I read that, but annual hydrograph is just a graph that shows how the river rises and falls throughout the year. So, let's say you get a lot of rain in summer, the river will be high in summer. And let's say you don't get rain in winter, it will be low in winter. So an annual hydrograph will show the seasonal characteristics, and its biggest influencer is the climate. So as said, seasons, climate, whatever floats your boat. Hardly ever gets asked in exams. You normally get asked the storm hydrograph, because the storm hydrograph is interesting. The storm hydrograph is used to show variations of river discharge over a short time period. This graph includes both discharge and rainfall on the y-axis. I'll just keep note of that. Okay, so here we have a storm hydrograph. So the discharge rate is measured in cumex, which is meters cubed per second. That's the unit of discharge. Okay. So if I extend this line here, why is it on that thing? If I extend this line here, that is the approach segment. So the approach segment is the discharge prior to the storm. So it will always be lower than the peak discharge. You can just think of it as lower. You can just think of it as how the river normally is when there is no storm. Okay. The rising limb shows how quick. What am I saying? Here's the rising limb, right here. The rising limb just shows a quick rise in discharge. So as said before there was a storm, discharge rate was low. Storm started, rising limb becomes steep. It just shows how quickly the river rose, or how quick the discharge rate rose. Rising limb is always before peak discharge. Okay. Bank full discharge is a line. Let me make it here. So here's the bank full discharge line. So bank full discharge line is a line that indicates the maximum amount of discharge that can occur in that river without a flood occurring. So anything above this line will result in a flood. So as you can see here, if this was the bank full discharge line, then there would have been a flood because the peak discharge is greater than what the river can hold. So the peak discharge is just the maximum river discharge. So it is the quickest rate at which water was flowing through the river. Okay, now we have lag time right here. Lag time is just the time between the max rainfall and max discharge. So to calculate lag time, you look at the time of the peak rainfall or maximum rainfall and the time of peak discharge. This time in between these two things is the lag time. A shorter lag time will result in a steeper rising limb. A longer lag time will result in a shallower rising limb. The receding limb or the falling limb is, I would say 99% of the time, less steep than the rising limb. This receding limb shows the discharge decline after the peak discharge. So peak discharge occurs, the receding limb or the falling limb is just the discharge after peak discharge has occurred. So it is always downwards. It always occurs after peak discharge, and you must just remember falling limb because it's falling off the top. Here's the peak, it's falling limb. Okay, now we get to storm flow. So storm flow is just the stream discharge after the storm. So storm flow is just what happens afterwards. So it's just this part here. If you exceed this, it's just that. And then, yeah. So right here, this quick jump in lag time is caused by quick flow. Quick flow is overland flow that reaches the channel quickly. This causes this steep lag time. Okay. Moving on, storm processes. So rain falls on a drainage basin in large amounts. Overland flow occurs because precipitation is greater than the infiltration rate. This causes the rising limb to build to a peak rainfall / discharge. After a few hours, overland flow reduces and stops. Through flow then contributes to discharge and stops floodwaters from going down as quickly as they rose. Later, base flow takes over and the river goes back to pre-flood level. So what I just explained there was basically how a storm hydrograph occurs. So let's say a drainage basin is just an area that feeds a channel. So every drainage basin will have one main channel. So here's the main channel in this drainage basin. This channel will be fed by a whole lot of tributaries, which are just small streams and rivers flowing from higher ground to this channel. This channel will always be at the lowest point in this drainage basin. So in a storm hydrograph, a storm hydrograph occurs when there is rainfall. This rainfall is everywhere and in large amounts, or it occurs for a long time. This rainfall will then cause overland flow because the precipitation rate is greater than the infiltration rate, or the soil is already saturated. So this causes overland flow, which leads to these inputs becoming greater. So overland flow just causes more water to go into the stream. The more overland flow, the higher the peak discharge will become, and the the more steep the lag time. So once this peak discharge is met and it is no longer raining as heavily, the peak discharge will decrease as overland flow reduces and eventually stops. Through flow will then contribute to discharge, and through flow is just the water that's gone through the ground, as I explained earlier, and that will just continue feeding the river. The river won't be as high as when it's being fed the overland flow. However, it will still be above normal. And then once this through flow goes away, then the river will be fed normally through base flow and its original through flow levels and channel. It will be fed by the channel flow, such as the streams and thalwegs. Not thalwegs, what's it called? Tributaries. Okay, pretty easy. So drainage basin characteristics. So shape and size. Small drainage basins respond quickly, so lag time is reduced. River channels in circular basins respond quicker than those in linear ones. So let's say the drainage basin's, it's a bad example, let's say drainage basin is small and in a circle, lag time will be very quick, or lag time will be very minimal. There wouldn't be a lot of lag time because all the water or all the precipitation in the system is fed directly to the channel, the main channel. Okay, now we move on to drainage density. Low drainage density causes long lag times because water has a few paths to take. Okay, so the quicker the drainage density, shorter lag time, longer drainage density, longer lag time. Drainage density is just the amount of, let me actually Google that because I'm not 100% sure. Drainage density. Okay, so drainage density is just how many rivers there are in an area, or how many rivers there are feeding that channel. I would think of it that way. So here's the area, here's the main channel. High drainage density will mean that there are a lot of tributaries and small streams feeding the channel. Low drainage density would mean that this channel is only fed by a few of these streams and tributaries. Okay, and that's why a low drainage density causes long lag times. Low drainage density means less water gets to that main channel. Okay, next we have soil porosity and permeability. So, impermeable surfaces result in a greater peak flow due to more overland flow. So, let's say in a city we have cement. Cement is impermeable. This causes a lot of overland flow. This overland flow goes quickly into the channel and causes the lowest lag times and highest peak discharge. Permeable surfaces such as chalk and gravel allow for a lot of infiltration and percolation. This causes less overland flow and increases the lag time and decreases the peak flow. Then we get stuff like clay. Once clay has become what's the word now? Once clay has become hygroscopic, which I explained earlier, it's just when the clay absorbs some water. It acts the same way as concrete and will no longer absorb or will no longer be permeable. It will become impermeable and cause more overland flow. This storm hydrograph is also influenced by rock type. So impermeable rocks result in quicker response time and lesser lag times and higher peak discharge. Permeable rocks like limestone. Remember limestone. If you get asked anything about rocks, mention limestone, because it's one of the best examples for a permeable rock, which means it absorbs water. Okay, so permeable rocks like limestone hardly ever produce storm hydrographs. This is because they absorb the water and hold it. Hydrograph is influenced by slopes. A steeper slope will mean more overland flow and shorter lag time and higher peak discharge flow. So steeper the slope, quicker water gets to the channel. And higher lag time. Less lag time, higher peak discharge. Yeah. Vegetation type, dense vegetation results in more interceptions, results in reduced flood response, which results in longer lag time, which also results in lower peak discharge. And then one of the main impacts on a drainage basin and the storm hydrograph is land use. So urbanization and deforestation increase overland flow. This increases drainage density, which means water gets to the river faster, which increases peak flow and lag times are reduced. Okay. Hopefully I'm recording this, so I'm not going to be pretty upset. Okay, now we get to a bit of an easier topic. River channel processes and landforms. Let me just find a picture of this graph here. Let me look for this Bradshaw model, because it's pretty good in my opinion. It explains things quite easily. Yes, type with one hand is rough. Bradshaw model. This isn't the best one. A bit better. Okay, here we have the Bradshaw model. So the Bradshaw model just shows how a river's characteristics change as it goes downstream. Okay, so Bradshaw model can be split up into three sections. these sections are upper course, middle course, and lower course. That's very bad. Upper course, middle course, lower course. So up, that's very, very bad. So up, mid, up, middle, and lower course. Okay, so as you can see, upstream in the river, there is not a lot of discharge. This is because the channel will merge with more channels downstream, and this increases discharge. The channel is not very wide. The channel depth is shallow. The average velocity is not too great. This is because there is a lot of turbulent flow. The load quantity is relatively low. The load particle size is greatest. This is because there is the most I wouldn't say that the velocity is low, but I would say that this is the quickest part of the river. This goes against what I just said about average velocity being lowest, but because there is a lot of power in this water and the water is very steep, the load particle size is greatest. Okay, just forget what I just said. Let me start at the bottom here. So upstream in the river, this is normally in mountains and hills. It's very rocky and it's very steep. So the gradient in the upper course of a river upstream is very, very steep. This causes very quick average velocity, or it causes a lot of turbulent flow. The channel bed is very rough. This is because it is mainly traveling over rocks and big boulders, and these boulders will take a very long time to be eroded, unlike the sand and clay further downstream. And then the load particle size is also greatest. This is because it's in mountains, lots of velocity, lots of power in the water. Yeah. Middle course is just an average between everything. Middle course has medium amount of discharge. It's not the widest part of the river. It's not the deepest part of the river. Its velocity is not the greatest. Its load quantity is not the greatest, but it has a mix of everything. So it has large particles, it has smaller particles, it has everything. The channel bed is a little bit rough as it progresses from upstream to midstream, and it smooths out as it goes along. And then the slope is not that great. It's not the shallowest, but it's not that great. Yeah, and then the discharge, and then we move down to lower course. Greatest discharge, widest part of the river, deepest part of the river. The average velocity is highest. The load quantity is highest. This load quantity will also have the smallest particles like sand, clay, and gravel. This is because it requires the least velocity. In downstream in the river, the bed is very smooth and the slope is shallowest. Okay, moving on to how much do I still have to go through? Oh my god, it's a lot. Okay, moving on to erosion. So let's start with abrasion. Abrasion is when a river bed and bank are eroded by the river's load. So here's the riverbed. Abrasion is caused when particles within the water hit the bottom of the river and hit the bottom of the river and hit the side of the river. This erosion is caused by mechanical impact of debris rubbing on the riverbed and sides. This increases with velocity, and the hardness or the density of these objects also influences how quickly abrasion can erode a riverbed. So just think of abrasion as rocks being picked up by the water, hitting the bed and bank. Moving on to attrition. Attrition is when these particles within the river bang against each other, break apart, creating smaller particles. These smaller particles bang into each other, creating even smaller particles, and this process continues. Okay, hydraulic action is the removal of loose material from the riverbed or banks due to frictional drag of water on the channel. So here's the bed, water flowing. What is that? Here's the bed, water flowing down this way. Now let me remove that, that's not very good. Water's going this way. We have a rock over here. This water will keep hitting this rock over and over. Hydraulic action, keep hitting this rock. Eventually, this rock will have too much force acting against it, too much frictional force acting against it, and it will become dislodged, and therefore it is removed from this area and pushed further along the river, where abrasion will take place and then attrition will take place. Okay, now we get to corrosion. Corrosion occurs when the minerals in rocks are dissolved by weak acids in the river and are broken down. So corrosion is just think of rust or something. Just think of rust and then just think of that happening to rocks. It's just when the rock is broken down by like chemicals. Okay, what else is there? Yeah, that's about it. So lateral erosion is erosion on the river banks. Vertical erosion is erosion on the riverbed. Rate of erosion depends on the amount of weight of load, velocity, gradient, hardness of geology, pH level, and human impacts. So the rate of erosion is influenced by many factors, such as the weight of the load, the velocity of the river, the gradient, the hardness of these rocks, the pH level of the water, and human impacts. Okay, moving on to load transport. What have I done so far? Done quite a bit, eh? Yeah. Okay, load transport. So let's start with traction. Traction is when large particles are rolled along the riverbed by the force of the water. Particles spend all or most of their time on the riverbed. So traction, here's a riverbed, here's a rock. This rock is moved along the riverbed, not really lifting, it's just pushed along, rolled along. And this occurs because the water is pushing it. Yeah, that is traction. So traction is when a particle is pushed along the riverbed. Saltation. Saltation is when gravel and small rocks hop along the riverbed as a fast current picks them up and a slower one cruises. A slower one causes them to fall back down. So let's just use the same diagram. So smaller particles. So saltation is smaller particles like this are picked up by quick velocity, picked up, and then when the velocity drops, when there's less velocity, they fall back down to the riverbed and bounce along. They just bounce along. So siltation is just when small particles bounce along the riverbed. Okay, you can think of it as like wind pushing a plastic bottle along a road. It won't just roll. When there's a gust of wind, it will be picked up a little bit and stop bouncing around. Okay, suspension. Suspension is when silt and clay are held up by the water. This gives the river a cloudy appearance, especially close to the mouth. So lower velocities are able to pick up small particles like clay and silt. These particles stay within the water column and cloud up the river, which make it look muddy and dirty. This can almost always be seen near to the river mouth, where there is a lot of sediment in the water. Okay, solution. Small minerals dissolve into water and flow with it. So solution, you can just think of it as like mineral water. It's just when salts and stuff are absorbed from these rocks into the water. Just absorbed by the water from rocks and stuff that are broken down and are transported downstream. Okay, now just capacity is the amount of material a river can carry, and competence is the diameter of the largest possible particle a river can carry for a given velocity. Okay, I'm not going to explain the Hulgenstrom curve. Actually, I will. I'll explain that curve quickly. I won't go into detail, but I'll quickly explain it. Because I've done a few past papers on it, so I understand it. Images. Let me just quickly. Okay. Okay, here we go. Hulgenstrom curve. Okay, it looks very confusing if you look at it like this. Okay, but I promise you it isn't. So the Hulgenstrom curve is a diagram that shows the relationship between the velocity of a river and the size of the particles that are eroded, transported, and deposited. It shows where the sediment will be eroded, transported, or deposited. So deposition occurs when there is a reduction in energy. Sedimentation occurs when sediment is dropped from still water. Okay, so here it looks quite confusing. However, it isn't. Let me see if I can zoom in. Okay, there we go. It's poor quality, however, just deal with it. So here we go. So this white column here, in the exam, it might not be colored in, but you will get these lines here. So on the y-axis, we have velocity. On the x-axis, we have the sediment size. So just remember that the smaller the sediment size, you can't really say that. Just remember that clay and silt are exceptions because they require a high velocity for how do I explain this now? I know how to do it, but I just struggle to explain it. Okay, so velocity y-axis, sediment x-axis. Clay and silt are exceptions because they are able to be transported in a suspension. As you can see here, that's the wrong thing. As you can see here, why is it in this? As you can see here, clay and silt can be transported in a suspension. You can say this because deposition does not occur. So this whole white area is the range in which the particles at the top, here the particles at the top, are transported as a suspension. This line here is the critical erosion curve, or critical erosion velocity needed to erode these different types of particles. as you can see, here's the peak, here's the maximum erosion needed, and then here's the maximum velocity needed for deposition to occur. Okay, normally they'll ask something like, what is the maximum erosion needed for what is the velocity needed for the erosion of fine sands? Then you would say here. So you would take this line, go along to the y-axis, and you would look at it. As you can see, 0.1. It looks confusing because there are so many lines, but it isn't. Each one of these is 0.1 on that, or it's addition. So how do I? Yeah. So look, here's 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1. Okay, and then it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then it comes in tens. So then it's 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, then it's in 100. So 100, 200, 300, 400, 500. So it's pretty simple. It just counts. So you just double this amount each time. Or you add this amount onto the next number. So it's 0.1, 0.2, and then this will be 0.1 plus 0.2, 0.3. Okay, and it just carries on. It's quite simple. So then, as I was saying, the maximum velocity needed, not the maximum, I mean the lowest velocity needed to erode a particle will be roughly 10.7, 10.8. No, I'm wrong here. It'll be roughly 18. Okay? Roughly 18, and then remember to include the units in your answer, because if you get asked this, you will need to include this unit and you will lose all your marks if you don't include it. So I was wrong there. So if they ask you to find the lowest velocity needed to erode a particle type, you go there, go down the line, find the lowest point, go along to velocity, and then you work it out. So this will be about 18 centimeters per second negative 1. Okay, that should explain it. Okay, now we get to flow types. So we get a river has 3 flow types, and you need to know these. So the river has laminar flow. Laminar flow is water that flows in sheets parallel to the riverbed, common on smooth surfaces. So laminar flow is just water flow that is straight. Laminar, straight along the river. Here's the edge of the river, goes straight down the river. The river looks very smooth from the side. There's no white water, no turbulence, no rapids. The flow is smooth. Then we get turbulent flow. Okay, turbulent flow is when water closest to the bed or banks is slowed by friction and is overtaken by the Tholweg. The Tholweg is just the line of fastest flow. So you can draw it like this. It's just water that gets interrupted, turns back on itself, flows irregularly, does not flow in straight lines, flows wherever it wants. This will cause rapids and it will cause the river to look rough. Okay, this is caused because, let's say this is the riverbed. Riverbed is rough like this, and this roughness will cause the water that hits it to flow in random directions. So the water will start flowing that way, some water will start flowing this way, and then this slows the flow of the water and creates turbulence within the stream. And yeah, and then we get to helicoidal flow. I don't know why, but they seem to ask helicoidal flow quite a bit. I'll draw it up here just to explain. So helicoidal flow is the horizontal turbulence produced I can't say. Helicoidal flow is horizontal turbulence that produces a corkscrew motion. The Tholvig moves both laterally from bank to bank and vertically from surface to bed during one rotation. Okay, so I can just explain it quickly here. So let me use a better color. Here's the river. The helicoidal flow is flow that looks like this. Okay, that looks very rough right now, but I'll explain it here. It's easier to explain if you draw like this. Okay, so here's the slip of slope. This is the slip of slope. It's a bad drawing. There it is. Here is the outer edge of the river. Outer edge, inner bank, water. Helicoidal flow is turbulence that is produced both laterally and horizontally in a corkscrew motion. So it looks like this. Okay, so that's helicoidal flow. It acts from in a meander if they ask helicoidal flow, or if they ask how a slip of slope is formed, or if they ask how an undercut is formed, or if they ask how a river cliff is formed. Draw this diagram. I drew it right here. You will get at least 1 or 2 marks just for drawing this, no labeling. Okay, so helicoidal flow is flow that produces a corkscrew motion where the Tholvig moves both laterally and horizontally, both laterally and vertically, from bank to bank and from surface to bed during one rotation. So what happens here is it erodes this, it cuts this, erodes it, and then the flow is slow as going back up, so this sediment is deposited here. Yeah. What else do I have to explain? Okay, so channel types. We get straight channels, braided channels, and meandering channels. So straight channels are normally artificial. They're just straight rivers, like perfectly straight rivers. Okay, very artificial, hardly ever find them. Braided channels are channels divided by islands and bars. They are found when a central sediment bar begins to form in a channel due to reduced stream flow or increased sediment load. Okay, so a braided river is a river with banks and bars in between, so sandbanks and bars in between the river. Okay, you see? So it looks something like this. Okay, these banks, sandbanks and bars are caused because the flow rate in the river decreased. There was more sediment in the river, and this sediment built up and built up and built up, and this eventually created the river to shallow, and peaks of this what's it called, deposition or sedimentation breached the surface of the water, causing these bars, which cause the river to become braided. And then meandering river. Here we go. So a meandering river is just a river that snakes and bends like so. It just bends, you know. So the channel looks like a snake with many bends. Factors such as channel slope, discharge, and helicoidal flow and load combine to create a meandering channel. So here I drew the cross section of a meander. Please go and look at it. I don't feel like explaining it now, but please go and look at it if you don't understand why it's formed or how this is formed. But yeah, that's what it looks like as a river. That's what it looks like as a cross section. So a meander is not formed because of an obstacle. Remember that. does not form because of an obstacle. If you put that in your answer, you will get an automatic 0 because it means you don't know what you're talking about. Okay, landforms. Landforms. What do I need to say for this? Okay, I'll just go through this quickly. I'll draw a little bit, but I won't really explain too much. I'll just read it. Landforms. Meanders. A pronounced bend in the course of a river. So, meander, that's what a meander looks like. Pools and riffles cause the tholweg to deflect. Where the tholweg is fastest, erosion occurs, and deposition where it is slowest. So river cliffs. This here is the river cliff. This here is the point bar. Point bar is shallow. River cliff is deep, and the river cliff is often undercut. So here's the undercut, which undercut means it's just, yeah, it's undercut. And then an oxbow lake occurs when a meander is cut off. So say a meander becomes too steep, a flood occurs, this meander gets broken. So what occurs, the river goes like this, straight past. Oxbow lake is the remainder of that meander. So that's what an oxbow lake looks like. So river continues going straight, the meander gets broken, and then the leftover water here forms an oxbow lake. Okay, so pools are just deep sections of a river channel with lots of erosion. Riffles are shallow sections of a riverbed where sediment is deposited. In another video I explained why. You can watch that if you want. It's just the video I posted before this. Okay, and then we get to waterfalls. I'm just going to put a picture on the screen because explaining it will take quite a while, and I don't feel like explaining it now because it's late and I'm getting lazy. Please paste the whole thing. Okay, perfect. There we go. Waterfalls. So waterfalls occur when there is hard rock over softer rock. Water flows over this harder rock, and the softer rock gets eroded. Eventually, the soft rock will get eroded so much that a plunge pool will form, and over time, this soft rock will form an undercut. The harder rock will collapse, and a deeper plunge pool will form with boulders at the bottom from this harder rock. And as this occurs, the waterfall will grow in size. The waterfall will become higher. Okay, so that's waterfalls. If you get asked an 8-mark question about waterfalls, it should be 3 marks. If you don't know what waterfalls are, then tough luck. So gorges are a deep-sided valley caused by waterfall retract. So this waterfall will, where's the thing? Over time, this waterfall will move backwards. Waterfalls are never moving forwards, they're always moving backwards. So once this waterfall has moved back far enough, it will create a gorge. So it will look like this. And yeah, that's just what a gorge is. Rapids are found in the upper course of a river. They occur where the riverbed is rocky and irregular. This causes turbulent flow and white water, and it is very dangerous. So if there are rapids in a river, it's just dangerous. So if you get asked something about rapids, just say dangerous, caused because of an irregular riverbed. Okay, floodplains. here's the river. Floodplains are on the outer sides of the river. So floodplains are flat land made up of a mixture of sand and clay, silt and gravel. Next to the river that gets covered by floodwater whenever the river floods. So here's the thing. There's normal where water normally is. When the river floods, there's whole areas underwater. All of the stuff from inside the river gets taken out and put all over here. This makes this land very fertile, and yeah, makes the land very fertile. And this is because sand, clay, silt and gravel are all moved onto the outer banks. So a lot of farming is done around rivers, and that's why, because it floods and then fertile soil gets moved to the outside. Yeah. So levees are a raised bank formed on a river at the lower course of the river. So to stop floods, levees can be built. So there's the river. A levee is just an extension of the riverbank that keeps the water within the river and stops floods. And then deltas are wetlands that form as a river empties its water and sediment into another body of water, such as an ocean, lake, or other stream. You get types of deltas, but we don't really need to dive into that. If you get asked deltas in your exam, don't do it. If in the last page of your exam, if you get asked about deltas, rather find another question to do and do that other question, because it is very difficult to find 8 marks from deltas or 15 marks from deltas, because it's just very repetitive and there's not a lot of information about them, unless you know about all of the bird foot deltas and others, and yeah, it's a lot of work. Okay, so now what are we doing here? Okay, so okay, so here we go. Human impacts. So catchment flow modifications. So humans cause deforestation. Deforestation reduces evapotranspiration. This increases surface runoff, reduces lag time, and there is less surface storage. This results in higher peak discharge. So deforestation causes more floods. So if you have a tree, why is it blue? Tree. People cut these trees down, and surprise, surprise, floods occur. Okay, afforestation is when people plant trees to counter deforestation. So that will reduce floods because they're just planting the trees that they took away from the areas. Urbanization. I'm just going to read this whole thing. Urbanization causes more impermeable surfaces, reduces infiltration and increases overland flow. Sewage systems and storm drains get water to the main channel quicker. Urbanization causes lag times to be reduced and urbanization causes lag times to be reduced, causes flood peaks to be increased. This is because there are more impermeable surfaces and water gets to the river quicker. And then by building on floodplains, the available flood space is reduced, so flood levels will rise higher and will cause more damage to the buildings built on these floodplains. This could be seen commonly in the USA. However, now with the very strict NOAA guides and guidelines, it is less common. Abstraction takes water out of the system artificially. Over-abstracting can cause drying up of rivers, falling of water tables, and saltwater intrusion in coastal areas. Channelization increases the capacity of a channel, so shorter lag times and higher flood peaks. Channelization lowers the risk of flooding because water is transported away quickly. Water storage, building dams. Yeah, it just controls water in an area. And then reductions in industry activity. So if we start using water from an area less, or using less water from an area, old springs can re-emerge. This can cause flooding and areas become less stable. Okay, so causes of river floods. Physical causes are heavy rain or persistent rainfall, rapidly melting snow or ice, impermeable soil and bedrock, coastal storm surges, lack of vegetation, natural discharges, or dam failure. Okay, so I'm just going to give some examples. So physical causes, heavy or persistent rainfall. An example of this is the Western Cape. Recently in September, they received very bad floods as a result of persistent rainfall and heavy rainfall. Okay, rapidly melting ice or snow. This can be seen almost every year in India as ice and snow from the Himalayas melts and increases the floods and increases flood rates. Impermeable soil and bedrock. This can be seen in a place called Exmouth, where they received a lot of rain in a short period of time, which caused the clay in the riverbeds to become impermeable, which caused the flooding of the town Exmouth. Coastal storm surges. This can be seen in the Mississippi floods when they had their hurricanes. The storm surges broke the levees, which caused flooding. Lack of vegetation is basically everywhere. You can just think of a place where deforestation has caused problems. And then natural disasters or dam failure, that can be seen as in Libya recently, probably about a month or two ago in Libya, when the dams failed and flooded the town, killing a few people. Okay, so human causes, urbanization, impermeable surfaces, storm drains, channel restrictions, all of these cause floods. Building on floodplains, yeah, of course, floods those buildings when a flood occurs and increases the flood level because there's less area for the water to go. Okay, and then farming causes floods because the areas around a river are no longer natural and are manipulated to the farm's liking. This can cause floods. Okay, impacts of river floods: death, damage, disruption, makes a mess. In lower income countries, there are always more deaths, less cleanup, and the cleanup cost is less. In high income countries, there are less deaths and a higher cleanup cost. Okay, flood prevention. So flood prevention can be done in 3 ways. I say the 3 P's: prediction, prevention, and post-flood plans. Okay, so here's some quick notes about that. So reoccurrence interval, how often on average a flood of a certain size is likely to occur. So that can be predicted. So when the time comes for a flood to occur, the people can be prepared. Flood risk maps can be created that show where a river is most likely to flood. Areas with a high risk can be calculated from these flood risk maps. And these areas with high risk should be prepared for floods, like flash floods, and these areas are areas below dams, areas subject to flash floods, and areas close to the shore. Okay, and then forecasting and weathering, use of weather satellites, and then yeah, just knowing when a flood is going to happen. You can do this based on the weather. And then here's some post-flood things: loss sharing, so disaster aid and insurance. So you insure your stuff against floods. This will reduce the impact. And then of course you get hard engineering and soft engineering. Hard engineering is engineering against the natural process. Soft engineering is engineering that works with the natural processes. So hard engineering is building stuff like dams, straightening the river, building levees, building reservoirs, building spillways, and making the channel wider. They are very common in HICs, however they are expensive. Soft engineering are always cheaper than hard engineering and use the environment to reduce flooding. They do this by planting marshlands, contour plowing, removal of sediment, dumping rocks and sand into or around the channel. And these are most common in low-income countries. So, and then we get to the land use zoning. So the NOAA in America has introduced land use zoning. So people are no longer allowed to build on floodplains as they are at risk and will cause damage to the natural area because they are building property on a floodplain. And then what else is there? Appropriate floodplain use. So this protects wetlands. Animal grazing land is situated near the river channel. Parks are built between rivers and houses. Critical buildings like hospitals and police stations and fire departments are built far as possible from flood. I can't even speak, I'm that tired. Yeah, I think it's time to end it. From possible flood prone areas. So if there's a river at the bottom here, mountain, the hospitals and police stations will be built on top here. This is because they are least likely to get damaged by a flood, and they are safe when a flood occurs. So floods the area down here. People have safety and people have help at the top of the mountain, at higher ground, and will no longer need to worry about a flood impacting them. Okay, I think I'm going to end it there. If you watched it, hopefully you learned something. I learned some stuff for geography, and yeah, feel good about my exam. Good luck, guys.